Okay, so we'll get started. Today's lecture begins part 3, the last part of the course. So anything I'm going to talk about today and next week will not be on the next test. Okay? We're already done part 2. So the next test just focuses on part 2. So the next test does not include part 1. It is just part 2. And since we're starting on part 3, then this will also not be on the test. The scheduled date for that test is kind of late in the calendar with respect to these lectures. And that's for a couple of reasons, but one is that we're kind of ahead of schedule. So then we should have no trouble scheduling time for a review session right before that test. But again, that's not happening for a while. So let's just dig in on part 3 lecture material. And part 3 focuses on control systems. And so what I'm going to do today is just lay out some of the basic concepts that we're going to return to for the remainder of this course. The lecture material that we cover for the rest of the course is about how the body controls itself and controls itself not just among an organ system like the cardiovascular system, but also, or not within just an organ system, but also across organ systems. So to really understand those control systems, we have to touch on some real basic control theory. Sensors, feedback loops, those kinds of concepts. So we've covered this so far. We've gone through each of these organs, and we've discussed at a tissue level and a cellular level and sometimes a molecular level how these organs function. So what we're going to add to this is a sort of level of control. So it's not just slapping the brain on the body the way it's shown here, but there's control at varying levels of organization as well. You can have channels function as controllers that are decision-making centers. You can have, we talked about the enteric nervous system. That is the nervous system around your digestive system that's making decisions and controlling the functions of digestion. And then, of course, you can have decision-making centers in the brain that are important for physiological functions. In all of these cases, you have similar parts, and we're going to see schematics of those parts that look something like this, and we'll use consistent coloring and shapes for those parts. And they allow for organ system control. And the example that we'll use once we lay out the basic names and functions of these parts is thermoregulation. So that's our first subject having to do with control. So when you see that word regulation, you can think of homeostasis. That is regulating a constant internal environment. We'll then talk about neuromuscular control, reflex actions, and other kinds of control related to things like locomotion, responses to varying levels of activity. Okay, so this includes exercise, but also just getting up and walking around, things you wouldn't necessarily identify as being exercise, but require an elevation in metabolic rate and physiological responses to compensate for that in order to maintain homeostasis. We'll consider salt-water balance and energy balance as well. Okay, so those are actually just some of the cases that we're going to consider in this context of control. And so let's talk about control systems initially abstractly. And we'll use the example of a car, okay? My daughter was stranded up. She's a 6th grader. She went up to Big Bear, and last night she was stranded up in Big Bear, and she's trying to make her way home right now. So this was her situation last night. And so what we have here is an old car with an old kind of climate control system. And the situation, you can think, the analogy here is basically like the interior of the car is analogous to the interior of your body. And so just like this car, you can go out in the world and experience the cold. And so we have an external temperature of 0 degrees C. And we want to have the internal environment be comfortable. And remember, of course, one big reason for having homeostasis is that the cells and the biochemistry of the cells are very delicate. They're easily perturbed by changes in temperature, pH, and other aspects of chemistry. And so in order for our cells to function well, we want to maintain those cells in a nice, stable environment. So temperature is a big one for that. So much like what you are comfortable, the kinds of temperatures that you're comfortable at in the interior of a car, you know, your internal body temperature has a comfort level as well. All right, so the goal here is to maintain homeostasis. We want not only to achieve a comfortable temperature, but we want to keep it at that comfortable temperature. And this is going to be achieved with a control system, okay? For this car, relatively rudimentary control system. It has a dial for fan. I still have a car, just not that old. It has the same kind of climate control system. And you have the ability to turn on the air so that it goes over the heat exchanger from the outside and then rushes into the interior. You got a little knob here for what temperature you like, which is a mixture of the air going over the heat exchanger and the air not going over the heat exchanger. Okay, so let's lay out the parts for a control system, using this as our example. All right, first of all, we have the stimulus. Okay, here it's not temperature, it's low temperature. Okay, temperature can provide a very different stimulus if it's a low temperature that initiates a very different sequence of responses from a high temperature stimulus. Okay, so not only do we have to define a variable, but also a range of intensities for that variable that qualifies as stimulus. Because when we start talking about the body, obviously, if you get really warm, you don't want to start shivering. Okay, that's a whole different response from you know, a high temperature or a low temperature. So same goes for the car. Here we have the low temperature stimulus. That's the cold cabin that you encounter as you first get into the car. So what's your response? Well, let's turn up the fan knob in this car. That's going to increase the flow over our heat exchanger. And then that's going to have what? A negative effect on the stimulus. And so this is the kind of iconography that we use. We put this little minus sign here because this action of flow and then the warm air that's generated by that flow, it has a negative effect. So this sequence of events end up countering this stimulus, the low temperature stimulus, because of course that warm air will elevate the temperature. All right, so this is our first example of a control system. It doesn't have many parts. It's pretty straightforward. We have a stimulus that initiates the action, okay, the cold temperature that you can feel. But then we just dial in the response at some level, okay? We put up the fan to 4, and we just let it heat up the cabin. So this would be what we call a feed-forward control. It's fast and it's simple, but it's not very intelligent. That is, the intensity of flow here is not dependent on the stimulus. We're not monitoring the stimulus and adjusting that fan temperature. We're just starting the system and letting it continue. So in addition to these kinds of schematics like we see on the left or flow chart, we also might monitor the state variable. That is the variable of concern here. Okay, so the variable is obviously temperature. And in particular, for this example, it's the internal temperature. So that's what we would take as the state variable. That's what we're concerned with. That's the reason why you kick in all of these actions in response to the stimulus. We want to change that state variable. And when we initially got in the car, the internal temperature of the car was the same as outside, 0 degrees C. And then we had this response. We turn on the fan. Now, if we just dial in a response that's, say, 2 out of 4 on the fan speed knob, then you might see a response like this. It's going to heat things up, and that would be sort of a medium grade response, versus if you crank it up to 4 or 5, then you get a high response. But note something here, that these are just linear relationships. Eventually that wouldn't continue because of the physics of the heat. The heater would eventually reach equilibrium with the cold coming from the outside and the heat leaking through the insulation. But at least initially we have a pretty linear response, and it's not modulated, okay? We just have this fixed action and we see that response. But we're not, again, adjusting the fan speed according to the temperature. Now, we might personally do that, as we get warm. We might manually override the system. But the system is essentially, aside from that, it's designed to just go in a feed-forward way. So another old car, but at that era, a more sophisticated one, would have, among the first cars, this Lexus would have a climate control system that was more sophisticated and actually paying attention to what the internal temperature is. And so what you can do, and I'm sure it's familiar for everyone now, is you dial in your target temperature, and it has the ability to monitor the stimulus and modulate the response, the airflow, according to whatever that state variable is being recorded as by the temperature sensor. So we have to add a component, which is a sensor. So the temperature is going to feed back onto that sensor, and then the sensor is going to report the temperature to a computer, okay, a decision-making center. And it's going to compare the current temperature against what you requested. Okay, and the difference between is called an error, and that's just how far away the current state of the cabin of the car is relative to what you requested. And the way this climate control system will work is if that's really different, if it's much colder than what you've requested, then the fan will be turned up to high and it will generate a lot of flow. All right, so in light of the fact that, again, the actions orchestrated in response to the stimulus have a negative effect, then we call this a negative feedback control. Okay, the fact that we have a loop here makes it a feedback system, where you have a stimulus getting detected, feeding back onto the response. That's what makes it feedback. And then the fact that it has a negative effect on the stimulus makes it negative feedback. So you can see here this is a more sophisticated system. As a consequence of having more components, and for neurophysiological systems that would translate to more synapses, and synapses require more time, then they tend to be more slow compared to a feed-forward system, and they're complicated. You got more parts. So, so one key variable here is, what is my set point? Okay, so if we're talking about thermoregulation for the body, that's your body temperature. That's the target. And so for the car, we've got 35 degrees C in this case. And if we look at the state variable as a function of time, just like in the first case, we start at 0. But as we kick this series of actions into high gear, then we begin to elevate that temperature. Okay, now we get to the point where the computer needs to start making some decisions, okay? It's not simply varying the fan in proportion to the temperature sensor. In fact, I sort of misled you a little bit. We're considering here a simplistic temperature controller. So this is more analogous to the thermostat in your house, where you either have the heater on or it's off. Okay, so instead of varying the fan speed, we'll just assume here, for the sake of simplicity, that it's an on-off kind of response. So initially it's on, that heats things up. Now here's where the decision-making comes in. Your thermostat has a certain maximum temperature at which it'll stop doing that because it's now getting well above the set point, the comfortable temperature that you requested. And so that we call that upper point the upper threshold. And so when the state variable reaches the upper threshold, then the fan, in this case, turns off. And that's going to cause it to now start drifting towards a lower temperature. Now it's maybe getting a little uncomfortable because it's well below the set point. And so it's hitting what we call the lower threshold, and that's going to turn the fan on, and it's going to go back up again. Okay, so you can see that this is going to create a situation where there are these oscillations in temperature, oscillations in state variables. That's not uncommon for control systems. The magnitude and the frequency of those oscillations are going to depend on how sensitive the sensor is, the tolerances for the decision making made by the computer. It might have to do with the physics of the the thermodynamics of, in this case, the car. Like the thermodynamics are going to affect the rate at which this temperature drops. Okay, so there are a variety of factors, and if you're talking about a completely different kind of control system, then those specific factors are going to differ. But just at this point, be aware that just because you have a negative feedback control system doesn't mean you maintain the temperature perfectly. You often will see these kinds of oscillations. Okay, but at the end of the day, we do have a situation where the response is modulated according to the sensory inputs to the system. That's what makes it different from a feed-forward control system, where that action was just initiated and it just plays out in a similar intensity no matter what. Here we've got a system that's paying attention to what the state variable is and modulating the response. All right, now here's a little bit of jargon that we unfortunately need. And these terms are general to all control systems, so we'll use them again and again despite talking about some very different things. All right, so those actions that are initiated by the computer, those are called the efferent pathway. Okay, they influence the stimulus. Okay, so anything along that pathway, you could call an effector organ. Okay, like the heat exchanger or the fan or even the flow itself. Well, the flow isn't so much of an organ, but it's more of an action. But if you had to, say, talk about a musculoskeletal reflex, then the skeletal muscles that are recruited in that reflex would be an example of an effector organ. On the sensory side of things, we also have a sequence. In this case, it just includes a temperature sensor, but you can have a variety of sensors and synapses, releases of hormones, whatever. All of those things that are on the sensory side, that is, that factor into the signal that makes its way into the computer in this case, that's known as the afferent pathway. Unfortunately, efferent and afferent are very similar words. Afferent refers to the sensory side. Efferent is the action side. And the computer we can more generically refer to as what's called the integration center. Okay, so it's integrating sensory information, but more importantly, it's where decisions are made in response to that sensory information. Okay, so we have this example here of decision making with regards to temperature. We have the upper threshold, the lower threshold. So the computer's behavior is governed by an algorithm, okay? A sequence of responses that are orchestrated depending on whatever the state variable is. So we can spell out, for this case, what that algorithm looks like, okay? And for any integration center, the fact that it's making decisions imply this kind of decision making. So those algorithms can get complicated or they can be quite simple. This one's relatively simple. It's saying that if the temperature is low, in fact below threshold, then turn the fan on. And if the temperature is high, above threshold, then turn the fan off. Oops, sorry. Okay, so it's an algorithm that operates according to two simple rules. And already things start to look a little complicated because you get this dynamic behavior, you're creating oscillations, all with a very simple algorithm with just two rules. Okay, are there any questions at this point? on negative feedback and these basic parts. Yeah.
For the upper and lower threshold, is that decided by the integration center?
The question is the upper and lower threshold decided by the integration center? Yes. Yeah. So we take the integration center as essentially a black box. In this case, it's a green diamond. And within that green diamond, it has properties that might be totally sort of hardwired. It's not as though you need to have a brain in this case, but it's an inherent property of that system that you have these upper and lower thresholds. Yeah. Now, it's conceivable they could be modulated, that there could be adjustments to those upper and lower thresholds. But we take them, I can't think of any example that we use where it's actually changed. So we'll just sort of treat it like they have this algorithm and that's kind of a fixed property. Yeah. Okay. All right, so let's just consider the example real quick that the algorithm in response to, I'm sorry. Now, everything I laid out just before the slide changed was a negative feedback loop to achieve homeostasis, in this case, the internal temperature of the car. Here we have a different situation. In this situation, we're going to apply a different algorithm. And this algorithm's rule is that if the temperature's high, increase the fan. Right? That wasn't what we saw a moment ago, where it was a low temperature stimulus that would cause the fan to increase. Here, it's increasing the fan speed. So what's that going to do? Well, of course, if we have, instead of a low temperature stimulus, a high temperature stimulus, then putting or driving airflow across a heat exchanger is actually going to have a positive effect on that stimulus. And so if this is the algorithm, we have a situation where there's a positive feedback loop, okay? The efferent response positively influences the stimulus, which then feeds back and drives it to increase the efferent response all the more. So if you look at the internal temperature, you get a very different situation. You start off at cold, and the rule here is if the fan is low, that's going to drive an increase in temperature. That increase in temperature is in turn going to stimulate a further increase in airflow, which is going to drive the fan even higher. And if you keep doing this on, then the positive feedback loop will drive the state variable to a very rapid rise. So positive feedback loops are characterized by rapid responses. Again, this high temperature here is sensed by the sensor. The computer is deciding, well, let's crank it up even more. And then that's further having a positive effect, which is driving it more and more. Now, positive feedback loops are rare in physiological systems. If the goal is to maintain homeostasis, this is the antithesis of that. But we do see examples because control systems that we're going to consider are not just always fixed, but sometimes we actually want to change the state of something. And sometimes we want to change the state really fast. Now, if this just goes on and on and on, then we have a system that might become chaotic or is not controlled any longer. So in order to shut this down, it requires an external shutoff. We have actually considered an example of a system just like this. And that was when we talked about action potentials. And we have inherent to the behavior of the voltage-gated sodium channels all of the parts that we need for the positive feedback as well as the external shutoff. So we talked about when the membrane potential reaches threshold here, that causes the activation gates to open, which further activates other activation gates of voltage-gated sodium channels in the neighborhood of this channel. And you see the state variable being the membrane potential having this incredibly rapid rise, right? So that's characteristic of a positive feedback system. So what does that look like? now that we have these parts for describing control systems? Well, it's the channel itself that's functioning as an integration center, which we see again here with our green diamond. That channel is positively influencing sodium permeability, which is in turn driving an increase in the membrane potential, which has a positive effect on the sodium channels, which cause an increase. It just goes on and on and on, and the set point is the threshold that initiates the whole process. Now, this has a shutoff because of the inactivation gate. So as we march through time, we can see that the inactivation gates of sodium voltage-gated channels close those channels and cause a drop in sodium permeability, which allows for the membrane to be repolarized via potassium permeability. In our new terms, we would call this the external shutoff for that positive feedback loop. Okay, so there are a couple of examples that we'll touch on of positive feedback loop systems. Here's a clicker question for you. What type of control system is used to regulate blood volume? A, feed forward, B, negative feedback, C, positive feedback. Okay, give me your final answer on this one. Okay, most of you got the right answer, which is B. And so even though we haven't said anything yet about blood volume, the tip-off here is the word regulate. Okay, regulate implies that we're maintaining a constant state variable, and so that is achieved by a negative feedback loop. All right, so to summarize these types of control, we have feed forward. They can initiate a fast response. They tend to be relatively simple control systems, having fewer parts, but the response is not modulated. And so we'll talk about reflex arcs later on. It's an example of a feed-forward system. Whereas those regulatory functions are achieved by negative feedback loops. They're more complicated, they have modulated responses, and we're already in the middle of talking about thermoregulation on that front. Finally, we have these positive feedback loops, which have very fast responses, but they require an external shutoff, and we have talked about the sodium voltage-gated channels for that.
Question?
Question.
So the external shutoff is what regulates the positive feedback?
No, so the external shutoff disables the positive feedback. So it's not really playing a modulating role. It's not really part of, it's sort of analogous to the way that a feed-forward system has to be initiated by something externally. And then once it starts, then the control system just plays out, and the thing that started it is no longer a factor in the control system. It's sort of independent of the control system. So for feed forward, you have something that starts it, and for positive feedback, you have something that shuts it down. Okay, that's what the shutoff is essentially doing. So it's disabling the control system.
Thank you.
Just to clarify.
Yes.
The external shutoff, is it independent from the stimulus or response, or
Is the external shutoff independent of the stimulus or the response? It can sometimes depend on the stimulus. Yeah, or it could just be engaged at some fixed period of time. It depends on the system. Yeah.
It's mostly not modulated, right?
Well, so it's a disabler of the system. It's not a modulator of the system. Okay, so homeostasis is achieved by negative feedback control. If you see the word regulate, it's implying homeostasis. Thermoregulation, pH regulation, blood volume regulation, blood pressure regulation, any of that, you can just, if you hear that word, you know that you should look for negative feedback. Okay, so just to continue on with the thermoregulation example, so let's just take the basic parts and see how they apply to an actual body. All right, so again, we've got the low temperature providing a stimulus. How does the body become aware of that stimulus? Well, one way is you feel it on your skin, and that's via cutaneous thermoreceptors, okay? You have thermoreceptors within your skin that make your body sensitive or responsive to a low temperature stimulus. Okay, that is compared against your body temperature by an integration center. All right, then we have a variety of responses potentially to that low temperature stimulus. So here's our algorithm for the control center, and that integration center is located in the hypothalamus. We'll show you where that is later. But we have this region of the hypothalamus called the hypothalamic thermoregulatory center, okay? And its algorithm is quite simply that if the temperature is below some lower threshold, then let's start shivering. Okay, so shivering is, muscle contraction is somewhat inefficient. And because of that inefficiency, shivering, there's a generation of heat as we generate force, and our body takes advantage of that effect to initiate shivering, and so shivering generates heat as a consequence of that inefficiency. So because skeletal muscle is involved, that tissue is going to be controlled, or its activity is going to be initiated by somatic motor neurons. We can call the skeletal muscle, in this case, an effector organ. And that effector organ is going to contract and relax, and have a negative effect on the low temperature stimulus. Okay, so thermoregulation, we see a negative effect. Our efferent pathway here negatively influences the stimulus, which is exactly what you should expect. All right, so that's about as simple as it gets for our physiological control systems. Now, we quite often will find that the body has measures to respond to a stimulus that operate in parallel. Sometimes there's gearing, so you'll have one type of sensor that is particularly sensitive and another one that's initiated at really high stimulus intensities. And we have that for the thermoregulation in the body. So in addition to feeling temperature on your skin, you more centrally can detect temperature. If you're so cold, this might be happening to my daughter right now, if you're so cold that your blood temperature starts to drop, then your body senses that and responds to it. So this low temperature stimulus can be detected by the hypothalamus itself. There are thermoreceptors in the brain that are sensitive to the temperature of the blood. And if those sensors are activated by a low temperature stimulus, then everything sort of goes up a notch, okay? Shivering has been insufficient to maintain temperature. And so now your body starts to do something else. And so it's going to, and we're less conscious of this because it's not recruiting skeletal muscles, but instead smooth muscles. And those smooth muscles are the arterioles that are just upstream of the capillaries that are in your skin, the cutaneous blood vessels. So when these are sympathetic neurons, and I'll explain what that means in particular later, but you're not conscious of their efferent actions, that's going to cause vasoconstriction to the skin. So if there's vasoconstriction to the skin, that means your blood is differentially shunted somewhere else, in particular into the internal organs. Okay, so this is a nice example of shunting and how if you have vasoconstriction in one region, then the blood's going to flow somewhere else. That also is going to tend to have a negative effect on the low temperature stimulus. And therefore, it's another negative feedback loop. It's just one that operates in parallel with the first one that's initiated by what you feel in your skin. So this is a simple illustration of multiple pathways, multiple parallel pathways that are recruited to maintain homeostasis. All right, so what about a high temperature stimulus? Okay, high temperature stimulus, you should expect totally different responses, and that's indeed what you see. Now, here I've eliminated the parts that shouldn't apply to a high temperature stimulus, and the rules are different. So in that hypothalamic regulatory center, we have, if the temperature exceeds an upper threshold, that we're going to do something to increase the loss of heat from the body. And we see here that we still have those sympathetic neurons that control the cutaneous blood vessels, but the response to a high temperature stimulus is vasodilation. So as you start to heat up, so let's just say you're exercising, so the elevation in temperature is coming from within, then you begin to send more blood through the skin and using the skin as a heat exchanger. So if the air is cooler than the internal temperature of your body, then especially if you sweat, then you can offload heat. And so we can see that even though we've reversed the direction of temperature, we've gone from a low temperature stimulus to a high temperature stimulus, we still have a negative effect. All right, so there's some kind of action here in red, and so long as it has a negative effect, then it's going to help on regulation. That's our goal. Now, since this ability to exchange heat or to offload heat is enhanced by sweating, then sweating also is an efferent response. And so we see sympathetic neurons that activate sweat glands in the skin that causes sweating, and then we have evaporative heat loss that is another action having a negative effect on high temperature. So a lot of this can be kind of tricky because you can have cases where there are double negatives. You can have like a low thing and you have a negative effect on a low thing, and you just have to be sort of careful about the direction of the stimulus and the effect of these effector organs. Question?
We've talked about vasoconstriction and vasodilation before, but in the lungs,
Yeah.
as like a parakin response to partial pressures changing, would that cause responses there as well if you get to high enough or low enough temperatures, or no?
There, where? In the skin?
Saying that, like, for example, these kind of reactions, the vasodilation, the vasoconstriction, when we talked about that before, it was in the lung, in the alveoli, but would the reactions here, would that affect that as well, or no? No. So the question had to do with whether or not, when we were talking about ventilation perfusion matching, and you have vasodilation and vasoconstriction, if those smooth muscles might also be recruited in response to temperature. And the answer is no. These efferent actions in particular only refer to the cutaneous blood vessels. And so this is a good point to raise because we'll see in the recruitment of these efferent pathways for some regulatory function, they're very localized and very specific. And there are some examples of the release. We're going to get into epinephrine release. And when that happens, you can have a whole suite of responses in the body. But this would be an example of something targeted. And so this is actually orchestrated by the release of a neurotransmitter via neurons. And so those responses are just very specific to, yeah. So, but it's a good issue to raise at this point that we have some responses that are quite global in the body and then others that are more surgical in the response. Okay. So what do we see here? The same pathways can be used in response to either upper or lower threshold responses. Okay, so we had cutaneous blood vessels getting involved for both high and low temperature stimuli. Or you can have pathways, efferent pathways that are specific to the direction of temperature or the intensity of the stimulus. Okay, so sweat glands are not recruited when you're cold, only when you're warm. All right, so we're going to continue with, so here we have thermoregulation in a very boxes and arrows flowchart sense, but we're being really vague about what it is in the body that achieves all of this. And so as we go through each of these control systems, we're going to sort of bounce back and forth between this sort of abstract thinking, which helps us make predictions about how we have state variables changing through time, but it's not so good in terms of getting specific details about how these things work. So let's take the example. So we've moved the thermoregulation where it's a response to a low temperature stimulus up in the top there. And let's just march through the parts that we're talking about for each of these boxes and arrows. All right, so first of all, the cutaneous thermoreceptors. So up here in the skin, we have a variety. The skin is sort of a wonderful sensory organ. There's touch sensors, they're responsive to pain, temperature, etc. So some of these dendrites are branching through and responding to a low temperature stimulus. And so we see that schematically here. Here we've got the skin, those dendrites. And what we see here is that irrespective of the nature of the stimulus, whether it's high, low temperature, or something else, those dendrites are going to collect up and eventually pass through this portion of your spinal cord. Okay, the cell body in particular, that's what's being shown diagrammatically, is that circle. The cell bodies on the sensory, for these sensory neurons, are all congregated around what's called the dorsal root. And if you look along your spinal cord, there are a whole bunch of these down the length of the cord between vertebrae, which is a nerve with a thickening just outside the spinal cord. That's the dorsal root, and it's thicker because it has to fit in all of those nuclei for the afferent neurons. And so its axon terminal terminates right here. Now, what we have here is a cross-section of the spinal cord. And it has this butterfly shape with a darker region in the center, okay? That dark region is known as the gray matter. The rest of it is the white matter. The reason why it has the white color in the case of the white matter is that myelination, we talked about that for speeding up action potentials, myelination gives the tissue a whiter, pearly color, whereas neurons without myelination have a darker color, okay? So the gray matter is filled with neurons that are unmyelinated. The white matter has myelinated neurons. Okay, a little bit of terminology. A neuron that connects two neurons is called an interneuron. All right, so what we want to do here is we're marching through our pathway. So we got these cutaneous thermoreceptors. They're activated by the low temperature. They want to transmit that signal to this integration center in the hypothalamus. Okay, so we're right here in our diagram on the arrow. And that brings us to this purple interneuron. Okay, the interneuron receives that stimulus. There is a chemical synapse right there. And in order to transmit that signal to the brain, it does so via this neuron, which is organized around what's called an ascending tract. Okay, so it's ascending if the signal is going up towards the brain, and it's descending if it's going from the brain down to the rest of the body. And myelinated axons can transmit their signals more rapidly. The reason why we have all of the myelinated axons in the white matter is because they're sending signals either up to the brain or signals from the brain down to the regions of the body that are going to respond.
Question?
Yeah.
So descending tract, gray matter, ascending white matter?
No. Gray matter are unmyelinated axons. White matter are myelinated axons. Among the myelinated axons in the white matter, you can have both ascending and descending tracts.
Thank you.
Okay, so the brain. All right, we're going to focus on the regulatory functions of the brain. We're going to ignore a lot of the other functions of the brain. Okay, so the brain, just for terminology, so the brain and the spinal cord, those are referred to as the central nervous system. Everything else in the nervous system is part of the peripheral nervous system. And so the thermoreceptors are part of the periphery. The rest of it is within the CNS. Okay, this neuron that's sending the signal up to the brain terminates in the thalamus. The thalamus is an integrating center, and it's also sort of a relay station for signals, sensory signals. And it can pass off those signals to regions of the brain that orchestrate a response. So here we see a 3D scan of the brain. The thalamus is right there. The anterior region of the brain highlighted in red. It's a relatively large region. In the case of thermoregulation, the thalamus activates the hypothalamus. Okay, so it's sending a signal. That's where we have our integration center for thermoregulation. So if we go back to our flow chart, we see that integration center right there. What does the hypothalamus look like? The hypothalamus is this little part of the brain. It has a very outsized role in regulatory functions. It's sort of this heart-shaped region right there. In response to that, we have the shivering that's activated. So somatic motor neurons need to be recruited. The signal for that originates from the hypothalamus. So we have a neuron starting from that region. And in order to activate motor neurons, it has to descend through the spinal cord via white matter. And then it's from there that they're going to activate the motor neuron. So the motor neuron, in this case shown in green, has its cell body right here. It has a chemical synapse to that interneuron that came down through the white matter. It's myelinated. And it's going to activate skeletal muscles to contract and relax, contract and relax. And as we already know about skeletal muscles, they use acetylcholine, and on the muscle side of things, they have a nicotinic receptor. Now, I mention that because the variety of pathways that are recruited for physiological systems can be distinguished by the neurotransmitters that are involved. So in this case, we call it a somatic efferent pathway. So the efferent pathway, again, is the response to some stimulus. And so this is one example. It's the one where we have a skeletal muscle that's involved. And with the last minute that remains, we'll consider the alternative, an autonomic efferent pathway. So for cutaneous blood vessels doing their vasoconstriction, we have a different descending signal that's sent, in this case to an autonomic ganglion, which activates a smooth muscle. And that smooth muscle, with the few seconds that are left, are activated by a different neurotransmitter. In this case, it's norepinephrine. Okay, we have norepinephrine acting on the smooth muscles, and then we have acetylcholine at this chemical synapse there. All right, so we'll take it from there next time.